So guys, some of you uh, emailed me about the question from the homework, uh, which was about chi-squared distribution. What I want to say is that I have not explained this. I will probably not explain this because we don't really use this distribution in our course. I may mention a few words about that, but I think I'll dedicate most of our time to something else that is very relevant in our course. So, as you all know, I will be extending the due dates of the homeworks, and whatever I have not explained, it might be because I don't consider them important for this course, or I may explain that in the future. So please be patient, do as much as you can, do your best, ask questions, and it will be fine.
Professor, real
Yes.
quick. So what are the homeworks due exactly?
So that the homeworks, as I remember, are due Wednesday this week, which is like in 2 days, September 16th, but I will extend it on September 16th by a week. So I will always be extending the homework, so you don't have to worry about it at all. So now let me start today's class. And we will go step by step. My class notes and the class slides are complementary, right? So you have to first read, understand everything that I am writing in class in my notes, and then also read the class slides, because the class slides give you more additional insights, maybe additional examples, but absolute must is what I write in class, and then the class slides. And then if you think you have more questions, maybe read the textbook. And of course, doing homeworks is very, very, very important. So now we will start our class, which is about chapter 3, and this chapter is about statistics. So we will review statistics in today's class, in the next class, and then next week. I think I may still have I think I'll solve problems for chapter 3, but does not mean that I will not solve problems even today. And then, guys, we will have our first midterm exam, which will be probably and very likely over the weekend of the next week. Very likely it will be on Sunday of the next week. Okay? And I will give you more details about that later. So you will realize that homeworks are very, very important. So please do the homeworks, because the exam will be based on the homeworks. Yes, please.
What if we can't make it on a Sunday for class?
If that's the case, then you can reach out. I will find another time for you. We can discuss that later, but there will be one time for everybody, but you can write it a day before or a day after. Like within 1 day, it's fine.
Oh, so like it could be like on Monday, the 28th, for example.
Could be on Monday as well, yes.
Okay, thank you.
No problem. Now, what I wanted to say is that 6 students are still not registered for Pearson. So guys, I'm not sure if one of those or a few of those are here who are not registered. But please register for Pearson's My Econ Lab as soon as you can, because otherwise I won't be able to help you, because homeworks are very, very important for this success in this course. So I will have absolutely no power to help you if you're not doing homeworks. That's what I wanted to say. Hopefully, if you are not here, hopefully you'll see this recording later and register for Pearson's My Econ Lab. So let me start today's class, which is about desires and statistics, and we will start from the very, very beginning. We already know a difference between sample and the population. Sample is a part of the population. Let's say population consists of capital N individuals or observations, whereas the sample consists of N observations. N is less than, and very, very often much less than, this capital N. If you guys do not hear me well, please let me know. Now, okay, let's say we have the following information. Let's say we are interested in a variable. Let's say that's the variable y. Let's say the variable y is, say, whatever. Let's say, I'll say something. Let's say this is, let's say, years of education. Okay, so that means that in the population we will have how many values? Y1, Y2, and so on, Y capital N, right? Are you guys with me? So that means that we have years of education for every person in our population, and the population size, as I said, is capital N. In our sample, we will have also values for every person in the sample. So how many the values we will have in total? Small n, right? Now, we assume that and this is in the heart of everything we are doing, that yi is IID normal with expectation of mu y and standard deviation of sigma y. I changes from 1 to n, capital N in this case. Can you guys tell me what this IID stands for? Guys, you see my blue screen, right?
Yes, sir.
So, okay, so first I stands for independent And second I stands for identically distributed. And the kind of distribution is indicated by this n, which is normal distribution. Okay. They are so yi, so this y1, y2, and so on, yn, those are independent with each other and also identical. Why are they identical? In what sense? Can you tell me in what sense are these y1, y2, and so on, yn identical?
In terms of like what they're measuring.
They, right? No, but in statistics, we say that they are identical in the following sense, in a sense that they are part of the same population. Do you see what I mean? They are part of the same population. They come from the same population because of that they are identical in that sense. But Shay, you can directly ask a question.
Yes, Professor. Just a quick question. So you're gonna just change the due dates on the eco assignment, right, Professor?
I will change the dates, yes, and the due dates, yes, but that will not happen today. They will happen on Wednesday, which is in 2 days.
Okay. So the Wednesday due date will be extended, right, Professor?
Will be definitely. So please don't worry about the due date because, as you know, guys, I always keep the promise. So I will definitely be extending the homework.
Got it. Thank you, Professor.
Okay.
Sure.
But now
repeat.
Yeah, so guys, this is really very important. I'm starting from the basics, but if you don't know the basics, you won't understand anything that we will explain later. So please follow and understand everything I'm saying. So what you want me to repeat?
You said identical because
I said identical because they come from the same population. I have just one population that can be like students of the New York City. They can be students of Baruch College. It can be anything, but they should come from the same population. If the observations can be individuals, can be countries, can be whatever, but in this case, individuals. Since they are part of the same population, then we can say that they are identical in that sense. Okay, now, how would you calculate expectation of y? That is what? Sum of what? yi times probability of what? Y equals yi. I changes from 1 to capital N. Okay? But probability of y equals yi is what? In this case, 1 over n. Guys, are you with me?
Yes.
Since these observations are identical and are independent from each other, then you can say that the probability of any of the yi is 1 over n because you have n observations, and if you want to pick one of those, then the probability of picking one of those will be 1 over n. So because of that, you will have 1 over n times sum of yi, where I changes from 1 to n. Oh my God. So, okay. Guys, what should I have here? Definitely not z, right? Because this should be expectation of y. Guys, are you with me? Please follow, because see, now I made a typo which may confuse you guys. So that's what I wanted to say. Expectation of y will be 1 over n times that. Right? And we denote this by mu of y. Okay. So what do we have? We have expectation of y, which we denoted by mu of y. Mu of y is another notation for that expectation of y. And that equals 1 over n times summation of yi, where I changes from 1 to n. Guys, up until now, are you with me? Is anything,
Yes.
is anything unclear?
Yes.
Okay. But this is what? This whole thing, okay, that mu of y is what? That's one of,
Expectation of y.
yeah, but that's one of the what? One of the,
The population.
very good, population parameters. Okay. There are others, we explained that before, but we concentrate on this particular population parameter, which is mu of y. But the thing is, the problem is, and that's the key, the problem is that we do not know the population parameter. So meaning in this case, we do not know mu of y. Why do you think we don't know mu of y? Because I mean, if you want to know what is mu of y, then you need to know,
The whole population.
yeah, then you need to know yi for every observation in the population. And that is very costly. Right? For example, if you want to know years of education of the students in the United States, then you have to survey every single student in the United States. And that is very costly. Are you guys with me?
Yep.
Because of that, you will never know mu of y, the true mean. That's what we call true mean. So what can you do then? That's
Take
why
samples.
you take a sample. And n is usually less and much less than capital N. Right? And then instead of, okay, you don't know mu of y, you will never know mu of y, but you can calculate what? X bar. X bar in an identical way, right? So what I mean by that is that not X bar, sorry guys. I'm saying y, and then I
In
suddenly
Y bar?
say y bar, yes. Very good.
So, Professor, so Y bar is the sample mean?
Yeah, true.
Okay.
So I don't know mu of y, but I can take a sample of size n, and is usually much less than the population size, capital N, and then I can calculate y bar, which is the sample mean. And this is the population mean, right? That's the expectation, another name of the population mean.
Professor,
Yeah.
I can't see the blue screen anymore. I think it like isn't sharing.
What about, guys, do you see my blue screen, others?
Nope.
I see you
Oh.
smiling.
Really? No. That's impossible because I have turned off the. Okay, guys. Do
You have
you
an
now
amazing
see?
smile.
Oh, thank you. Do you now
Okay,
see?
now it's here. Yeah.
Okay.
Yeah.
So let me repeat. So mu of I. Mu of I, that's the population parameter. We don't know that because we don't have the information about all the observations in the population. That's hopefully understandable. And that's why we take a sample of smaller sample of size n, small n, much less than capital N, that's the population size. And then we calculate Y bar, that's the sample mean. But expectation of Y is also known by population mean, but Y bar is sample mean. Y bar is a sample analog of the population mean. Am I guys clear?
Yep.
And you calculate this in an identical way. So meaning that I mimic whatever I did here. So I do this 1 over capital N, sum of yi, I changes from 1 to capital N. Now tell me what is my mistake.
Do we use capital N?
No, that's why no. You are mimicking this transformation, but
You need lowercase.
you need lowercase n. Am I clear? And that is something that you can calculate from your sample. Because you have information about every observation in your sample, simply because you just survey a smaller sample.
Wait, so
And
YI would be like year 1, year 2, year 3.
no. I would be, so no. Why I would be like, why I started it here like, was it not I clear? I said Y is just a variable. That's years of education. Y1 is years of education for the first observation. Y2 is the years of education for the second observation, and so on.
In a sample, would the Y be lowercase, Professor?
No. Because see, so the thing is, I see what is your confusion, but see, those are the like sample is just a part of the population, right?
But
Oh,
Professor,
right, I
Like,
understand.
so these Ys are the same Ys, but Y1 is not necessarily, so this is like first observation in your sample, but that's first
Right.
observation in your population. They are not necessarily equal, the values.
what is the numeric representation of YI?
Sorry, what? Can you please repeat?
What would be in place of YI if you were to replace it?
Number,
Like,
for example, let's say you are the first observation in my population, not in my sample, and your years of education would be Y1. Let's say I am second observation. Let's say I am 2. Y2 is my years of education. Let's say I have 17 years of education. Let's say you have 10 years of education. There will be numbers. Am I clear?
Yeah.
Okay, then. So now I think we are clear on that, but I can also, of course, listen to the recording, and this note will also be available. So to summarize, we started from where? That yi is distributed identically, independently, and normally with mean of mu of I and standard deviation sigma of phi. So these are just numbers, right? Okay. What is mu of phi? I gave you the expression for that, right? So let's say this is your population, this is your sample. Okay, then mu of phi is the same as expectation of phi, so this is also denoted by mu of phi. That's what is here. And that's, you already know, that's 1 over n times summation of yi, and I changes from 1 to capital N, but you don't know this. Okay, I don't know this, but then I can take a sample of size, here sample size, here population size is n, I can take a sample of size n, which is much less than n, and then I can calculate y bar in an identical way. So, and that will be 1 over small n times summation of yi, where I changes from 1 to your sample size. That's all. That's all. And then, so y bar is what? Sample mean. Mu of y is the population mean. This is unknown. But we know sample mean. Why? Because we can calculate. Okay, and then, we don't know mu of y, but y bar, the question is, y bar definitely is what? Is a sample analog of mu of phi. But the question is, how good is y bar? It's like y bar is an estimator of mu of phi. Guys, are you with me?
Yep.
The question is, are you interested in y bar or are you interested in mu of phi?
Mu of phi.
Exactly. So, yeah, that's true. We are not interested but we are interested in knowing mu of phi, but that is an impossible task. And what you do, you just do your best. Just like meaning to get the best possible estimate of mu of phi based on your sample, based on our sample. Okay, and then there are a number of estimators for mu of phi. One of them, and in fact, the best is what? Y bar. Can you tell me best in what sense?
The closest to the actual population mean.
Okay, that's one of those. Okay, good. So now we will list the criteria or requirements a sample, an estimator should satisfy to be considered the best. And the requirements are: the estimator should be unbiased. In this case, the expectation of y bar should be the true mean. Second, should be consistent, which means that variance of y bar should go to 0, okay, when n goes to infinity. And third and the last requirement is efficient. Which means out of the two estimators, the one that has lower variance is more efficient. Now, let me first, okay, let's say consider two estimators. Okay, let me of the can you tell me? The first candidate is which? Y bar, right? Clearly. Can you tell me which one is the second candidate? Y16, right? Do you agree with me? But maybe
Can you
Y.
explain? Can you
Maybe,
explain what Y16 is?
yeah, so Y16 is an estimator of the true population mean because Y46 also the estimator. Because Y616 is also an estimator. Anything, right? But it is shown that Y bar is the best. So let us check. So any yi is also from your sample is also an estimator of mu of I. But all of them are inferior to Y bar. And let's see why. So let's check if Y bar satisfies the requirements. First of all, what is the expectation of Y bar? Okay, that's expectation of what is Y bar?
Y isn't y bar average?
1 over n times summation of yi. And that is 1 over n times expectation of what? The summation of yi. Then that is what? 1 over n times expectation of y1 plus y2 plus and so on plus yn. But then expectation is a linear operator. So how many, okay, so that's 1 over n times expectation of y1 plus expectation of y2 plus and so on plus expectation of yn. Now I will check if you were like carefully following whatever I'm explaining. So what is expectation of y1?
Is it mu?
Very good. What is expectation of y2?
Is it mu y2?
Mu of y. What is expectation of yn? Again, mu of y.
Mu y.
Why? Now let me ask, why? Because we started from the assumption then that expectation of any of the yi is mu of y. And I said, this is our starting point. Did not I say that? Guys, expectation of any yi, this is y15 or y16 or whatever, is mu of y by assumption. And so, okay, then how many mu of y's do we have here?
N value.
So we have 1 over n times mu of y. Do you agree with me? And then these n's cancel out and you are left with mu of y. So we obtained that expectation of y bar is mu of y. So is it unbiased?
Nope.
Why? Because what does unbiasedness mean? This, right? So it is unbiased. Yes. So we have it. This is like check. Now let's do the same thing for let's say y16. What is expectation of y16? Mu of y by assumption. So unbiased? Yes, unbiased. So check here as well. Now let's check if y bar is consistent. So then to check that, we need to calculate variance of y bar. Guys, just let me know that you are here and that you are following. So very
Yeah,
good.
scroll up for a second.
This will be what? 1 over n summation of yi. I changes from 1 to sample size. So this will be 1 over n squared times variance of y1 plus y2 plus and so on plus yn. I said y1, y2, and so on, yn, those are independent. So because of that, you can write the following times variance of y1 plus variance of y2 plus and so on plus variance of yn. And if y1, y2, and so on, yn, if they were not independent, then what else would you have in this expression? Guys, if y1 and so on, yn were not independent, then what else would we have in this expression? Guys, covariance terms. But since they are independent, then the covariance terms are not there. So we have 1 over n squared times. What is variance of y1? Sigma squared of y. What is variance of y2? Sigma squared of y plus so on, plus what is variance of yn? Sigma squared of y. Why? Because remember our assumption that yi is IID normal with mu of x and standard deviation sigma of y, mu of y standard deviation sigma of y, but standard deviation sigma of y means that the variance of yi is sigma squared of y. So how many sigma squared of y do we have here? N. So then we have 1 over n squared times n times sigma squared of y. This n will cancel here, and then you will have sigma squared of y divided by n. So then we have what? Variance of y bar we obtained equals sigma squared of y divided by n. So then is y bar consistent?
Yes.
Why? Can you tell me why?
Because variance of y bar as you reach infinity is supposed to be 0.
This is constant. So sigma squared of y is a constant.
Oh.
So when n goes up, when n goes to infinity, what happens to variance of?
You reach 0.
Yes, because this y sigma squared of y is constant, this will go to 0. So then it means that yes, y bar is consistent. Check. So now what about, remember y16 we had before y16? Variance of y, is y16 a consistent estimator of mu of y? What is variance of y16? By assumption that is sigma squared of y. Consistent or not?
Yes.
Why?
Because, oh
N
wait,
goes to infinity. What happens to variance of y16?
wouldn't it reach 0 as well?
No, because where do you see n here? It is always sigma squared of y.
Oh, I see. Got it.
It never goes to 0. It is some constant, there is some constant. So, and so then means that not consistent estimator. So then means that y bar is superior. Do you see why? You don't even have to consider efficiency. Okay? Because we said y bar is consistent, y16 is not consistent estimator of mu y. So y bar is preferable. Guys.
Professor, so
yeah.
what are you like what are you trying to prove when you like do all this? Like,
I am just showing that y bar is preferable estimator for mu of y over y16 and anything else.
because it's preferred because it meets all three of the criteria you listed
That's
earlier?
exactly right. That's exactly right. So this already violated consistency.
Okay.
Professor,
But this, yes.
can you please show again why y bar is preferred to y16?
First of all, we showed that both of them, y bar and the y bar and the y16, both of them are unbiased. Then we showed that y bar is also consistent because when n goes to infinity, variance of y bar, which we derive this variance of sigma squared of y divided by n, sigma squared of y is constant, goes to 0. So that means y bar is a consistent estimator of mu y. But then, okay, what about y16? Variance of y16 is always sigma squared of y, because by its definition that we made above. And is it consistent? No, because whatever n is, when n goes to infinity, to be more precise, not whatever n, when n goes to infinity, y16, the variance of y16 is always sigma squared. Does not go to 0. Do you see? So because of that, y16 and any y I is not a consistent estimator, so that violates the second requirement, the consistency bar. So y bar, simply because of that, is preferred over y16 and any of the yi, right? Am I clear?
Yeah, thank you.
Yep.
Okay, so now what about efficiency? So we don't have to check this because we already, so y16 already violated the consistency requirement, but okay, then, okay, let's simply, for the sake of exercise, let's check which one is more efficient. So what is variance of y bar? We said that's sigma squared of y divided by n. What is variance of y16? That is sigma squared of y. Which one is more efficient?
Y bar.
Why?
Because if you divide by n, you have a smaller number than sigma squared of y itself.
What if n equals 1? Are you here?
Then they're equal.
Yeah.
The thing is, he was absolutely right. So y bar is more efficient. Simply because, why?
More consistent as
No, more
Being
efficient.
divided.
More efficient because,
It's being divided by n.
yeah, but what if n equals 1? Then they are equally efficient.
Yeah.
Because now a rhetorical question. Do we ever take a sample of size 1?
No.
No. So n is always greater than 1, and it is much more than 1. Because of that, y bar is always more efficient than any yi. Okay. So because of that, y bar is shown to be the best possible estimator of mu of phi. Guys, so what I would recommend is, even though we explain, this is not difficult if you understand, but I cannot emphasize how important it is to understand everything that we explained today. Because otherwise, you'll have a lot of gaps in your minds and you will not understand anything that comes later. So please take your time to understand everything that we have explained today. Okay. Now, so before I start a new topic in this chapter, maybe you want to ask questions. Do you guys have any questions or confusions or anything? So am I clear in explaining stuff? If not, I can re-explain, so that's not a problem at all.
Isa has conic.
Sorry guys, sorry, I hear a lot of noise. If you are not asking questions, then...
Maybe I should have gotten the Oreo. Oh, you like Oreo? I don't usually, but I feel like I'm craving it.
Okay, so you guys are...
You can mute her, Professor.
So just mute everyone.
Yes.
Oh, we are.
Yeah. How do I do that? I just...
We should just do a Zoom call or something together and then do it in one city.
Yo, your mic is on. Who are talking about Oreo?
Wait, you only
So
ordered 4? I thought there was more.
I
There's
am
more of
trying
us.
to understand. Oh, so sorry.
Professor, just mute everyone.
Mute everyone.
I am
Yeah.
trying. Where is that? I don't know.
My mom got it.
This is Taro. No, that's Wait, Taro. I think this is Taro.
Oh.
Wait.
Oh my god. Yeah, how do I mute everyone? Let me stop sharing. And then I'll be able to put on mute.
The green tea one looks more. Oh, they're working.
Okay, now I see. Now everybody is mute. But I now have to share the screen again. I should be able to do it without. It should be somewhere here, but I was not able to see it before. Whatever, it's okay. Okay, so guys, next. So next Wednesday, we will still be explaining stuff in this chapter. On Monday, I will do exercises from this chapter. On Wednesday, I will do more exercises from chapter 2 and 3. And then on Sunday, you will write the first midterm exam. Okay, that's the goal, but I will give you guys more details about this by announcing all of these details on the CUNY Blackboard. But remember, next week, not this Sunday, but next week on Sunday, we will have our first midterm. Now let me...
Is it at a specific time?
Sorry, what did you say?
For the midterm, is it at a specific time, or can I like complete it in the evening? Or
It should be done. I will set it in the morning, but if the morning is not convenient for you, we can reschedule it. Like I was thinking about having this midterm at 10 a.m. If it's too early, I can do it like at 11 or 12.
10 is good.
So 10. I think 10 is better. But I mean, if wants to do it later, that's also fine. So now let me talk about the distribution. So we will be, like throughout the course, we will be using the following distributions: normal, student Steve, and F distributions. Let me start by explaining normal distribution. Normal distribution function looks like this. The density of the normal distribution looks like a bell. Symmetric bell. So here I have this y bar, and then this is a, I really tried to have like a symmetric shape, bell shaped distribution. That's how the density of the normal distribution looks like. What do I have on this vertical axis? We have f of y. F of y has a complicated expression. But we don't use it. We use tables. That I will explain later. Can you guys tell me the value of the area below this density function? So the shaded area equals 1.
Is it 100? Oh, okay.
Yes. Now, now let me draw this again. Okay, we have y bar here, and so we want to know mu of y, but we don't know it. Let's hypothesize that mu of y is mu 0. So then we have hypothesis H null that mu of y is mu 0. If you hypothesize something, you have to also specify what is the alternative for that. The alternative is that mu of y is not mu 0. because mu 0 is whatever you are thinking mu y is, but mu y can be a different number. Of course, we have examples on that. I will solve examples next Wednesday, but now I'm just giving you like ideas about this. So we don't know mu phi. Let's hypothesize that mu phi is mu 0. So then this is how you formally write the hypothesis. We have H null, which we call the null hypothesis. And we have HA, which we call the alternative. Hypothesis. Sometimes instead of HA, sometimes we could use H1, but that's not a problem. Sometimes they use H1, but I always use HA because I prefer that, because that's like clear. Okay, mu phi we hypothesized that mu y equals mu 0. I mean, if you know me, this is something you hypothesize. This is something you are thinking mu of y is. If you knew the if you knew the value of mu phi, there would be no question. It is either equal to mu 0 or it is different from mu 0. But we don't know mu phi, that's the problem. But we still want to see if mu of y is mu 0 by some confidence. Okay, and then what we do then? So we do not know mu of y, thus we don't know whether mu of y equals mu 0. But we still want to be able to make an inference about whether mu phi equals mu 0 or not. Okay, you never know mu phi, that's why you will never be able to say something about that exactly for sure, but okay, then I don't know mu phi, then I have to do my best. Okay, what is my best?
Sample.
Exactly, so take a sample and calculate what?
Y bar.
Why? Because y bar is best possible estimator of mu phi. So if you can, so that is your best, right? So you are just using the best possible estimator of mu phi, which is y bar, to say something about mu phi. That is your best. You don't know mu phi. You cannot know whether mu phi equals mu 0, but at least I can say something. If instead of mu phi, I will use its best possible estimator and compare it to mu 0. Guys, am I clear?
Yep.
Then, Okay, so then I can compare y bar to mu0, right? So if y bar is different from mu0, then I can say if I am able to say that y bar is different from mu0, that means that mu of y is likely to be different from mu0. Are you with me?
Mhm.
But you are seeking for the difference in terms of standard deviations. So you are dividing that by the standard deviation of y bar. And this is what we call test statistic. Okay. Guys, so I will write something and I will finish today's class by that, and we'll continue next Wednesday. Before that, please take a very careful look at, if you can, whatever we did today. If the test statistic is large enough, means that y bar is far enough from mu0, and since y bar that we already showed is the best possible estimator for mu phi, then you can say by some confidence that I will explain later that mu phi is far enough from mu0, so it cannot be mu0. How far is determined by the critical values and we have 3 common critical values. That correspond to the 3 confidence levels. Not remember, but note that 1 minus confidence level equals the significance level. The 3 common confidence levels are significance level, critical values. have time, so I don't have to.
Professor,
Yes.
is this all part of hypothesis testing?
Yeah, that's all part of hypothesis testing. If there's anything you don't understand, just follow. I will be re-explaining stuff over and over again, so I don't have to worry about that. I'm just trying.
Are we going to do hypothesis testing in this class?
Not today, but we will. So why do I have this? I have no idea where this like yellow line comes from. Looks like it's not. Looks like it's not on the Word document, something like that.
Try erasing it.
I'm not able to erase it. Oh, okay. So 3 possibilities. Oh, good. So it erased automatically. 99%. So 1%, because 100 minus 99, and this is 2.58. 95%, 5%, 1.96, 90%, 10%, 1.645. That's, this table is valid.
Professor, is this the T table or something?
This is table 1 that I have not yet explained.
Oh, okay.
This is not the table that I have not. So I will continue from here next Wednesday. That's all for today, guys.
Professor, I had a question.
Yes.
So you said for the test statistics, we divide by standard deviation of y bar.
Yeah.
Can you repeat why that is again?
Because you are interested in mu y, and the y bar is the best possible estimator of mu of y. So if you are using y bar, then you have to divide this the numerator by the something that is about y bar. I said standard deviation, so you have to divide the standard deviation of y bar.
Got it. Thank you.
But then we also showed that this is sigma of phi divided by n, square root of n, right?
Mm-hmm.
Because we showed that variance of phi bar is what? We showed that this is sigma squared of y divided by n. Then okay, and this means that standard deviation of phi bar will be sigma of phi divided by square root of n.
Got it.
Okay, guys, thank you. So I will stop I will stop recording and also sharing my screen, and I wish you a good day.
You too.